Hello, mathletes. So section 3.2, talking about derivative functions now. So instead of just being able to find the derivative at a point, now we're going to talk about the derivative function in its entirety. And so if you notice the formula here, or the definition of the derivative function, is the same as we saw before, except instead of an a here and an a here, we have an x, right? So instead of a constant, we have a variable, right? So instead of getting an answer that's a real number, we're going to get an answer that is some type of function in terms of x. All right, and so the formula is pretty much the same, but as we work it out, we're going to end up with a variable expression most of the time. Sometimes you can't have a constant, but for the most part, we're going to have some type of variable expression, some type of function. And so our result, instead of f primed at a certain value, we're going to find f primed of x. And so it'll basically give us a function of all of the instantaneous rates of change along the whole function, right? Or all of the slopes of the tangent line along the whole function. Okay, so it'll give us a collection of points instead of a single point. All right, so this is the formula. Remember, this is f prime is what we call that. Means the derivative of f, and and so let's see down here. I want to include this. So differentiable. That means you can take the derivative of it, right? So if it's differentiable, that means you can differentiate it or take the derivative of it. So derivative and or to derive or to differentiate, those are both synonymous with one another. And so here we see that a function is said to be differentiable if the derivative exists at a point A, right? And so if a functional is differentiable on the entire function, that means it's differentiable on the whole, on every point or every input value. Okay, and so a differentiable function is one which the derivative exists on the entire domain, right? On the whole domain. So for every x value, f primed works, right? So you could take f primed of any value along that function and it works. That's a differentiable function. Okay, so that means we can find the derivative at any point. And we'll come back to this idea too of differentiability, and we'll talk about it in relation to continuity and in relation to finding limits as well. All right, so let's actually find the derivative here using the formula we just saw. So I want to find f of x. I want to find f primed of x, actually. So I want to find the derivative. So I want to find f primed of x. And I know that f primed of x, the formula is the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so first f of x plus h, I'm going to plug that in. And so if I put x plus h in there for x, then I'm going to end up with root x plus h, right? That's what f of x plus h is. And then minus, and then f of x, this is pretty straightforward, right? Because we actually know f of x already is just root x, right? So that's just f of x. And then I'm going to put that all over h, and we're going to bring down the limit as h approaches 0, right? And as usual, we can't just plug in 0 because that would give us a 0 in the denominator, and we can't divide by 0, and so we'll have to simplify this, right? So this is a radical situation. So what we want to do is multiply by the conjugate of this radical expression. So I'm going to multiply by root x plus h plus root x, and I'll do the same thing on the bottom to balance it out. Okay, and so then on top, we'll get a squared minus b squared, so it'll be x plus h minus x, all over. Then on the bottom, we have h times the quantity of x plus h plus the quantity of square root x plus h, or the square root of the quantity of x plus h, I should say, plus the square root of x. And so then we can see our x's cancel out here. And so we just end up with h all over h. And then our binomial there. And so now we can see the h's are going to cancel out, right? And that puts us in a good spot because now we can actually directly evaluate this limit. So we have a 1 on top, and then we have root x plus h plus root x. And if I plug in 0 now, I'm not going to end up with the denominator equaling 0. I'll end up with just, a real defined value. And so I'll have 1, and then here I'll have x plus 0, root x. And so what we end up with is 1 over root x plus root x. And when we add root x plus root x, we get 2 root x. And so this is our final answer. So that's f primed of x is 1 over 2 root x. So the cool thing about that is now that we have this function, now we can find any point that we want, right? So if I want to find like f primed at 2 like we did before, I can just plug it in here, right? If I want to find f primed at 3, I just plug 3 into this function that I have. So it's more versatile and comprehensive, right? We're getting not only not just a single value, but we're getting a function that represents all values, right? So we can just plug in any input here, and that'll give us the derivative at that point, or the instantaneous rate of change at that point, or the slope of the tangent line at that point.